That's mu sub naught.
Okay.
What he said.
Mu sub blob is all I could have gotten out of it.
Sometimes you'll see the little stem on the other side too, but yeah, the left side is longer. This is indeed mu sub naught.
Is that R cubed?
Where are you looking?
Under the cross product.
Oh yes, that's R cubed.
Yep.
There's actually 4 variations of the same thing. But mu sub naught is known as the permeability of free space. Or if we drop the 0, then it's permeability of whatever the medium is. Just as with dielectrics, if I have a dielectric between 2 parallel plates, the dielectric will react to the electric field, and that is measured in something known as permittivity. If I have a magnetic field and I put something near a magnetic field, it will react, and how it reacts is measured in something known as the permeability. It would have been really nice if they had chosen 2 words that did not sound anything like each other at all, but they decided, what the heck, let's do the same. That kid's having a great time. All right,
So
Brooke, you had a question?
Yeah, you said it's the magnetic field of from a moving charge, right?
Yes, magnetic field from a moving charge. Because ultimately, that's what creates a magnetic field, is a moving charge. Yes?
in the numerator, that was hard. In the numerator on the right, that's a cross product there with
Yes, it
velocity
is.
and something. Yes.
It's a cross product between the velocity of the charge and this is a radial vector. So if I have a charge Q that's zipping along like that, I want to know what's the magnetic field at that point.
Right.
Well, R would be a vector from wherever the charge is at that moment so if the charge is there at that moment, then that's R.
Same R that's in the denominator.
Yeah, this is the vector R, and that's the magnitude of R.
Okay, right, got it, thank you.
Now, just for a little bit of math fun, and I know that's a little redundant.
Yes, yeah. Or a paradox.
So, somewhere in the middle of the night, I'll think of a proper response for that.
Yeah. It'll hit you in the shower. And you'll be like, oh, damn it.
One more missed opportunity. The next season, I'll have it ready.
Yeah.
All right, what are the 2 things that all vectors have?
Direction.
Yeah.
All right, so the magnitude of R vector is R. The direction, we can just create a unit vector called R hat. The same is true for any letter. If I have some vector A, that's A times A hat. So instead of writing R hat there, I could write it as R vector, I could write it as R hat. That R would cancel out with one of those. And so this equation right here could also be written mu naught over 4 pi Q V cross R hat over R squared. So those are 2 variations of the same thing. If you start working through it from a math point of view, personally I find this one's a little bit simpler than that one, but in actual practice, go with the one that your brain is working on at that moment, and you get the same answer. Now there's 2 other variations of this, but before we get to that, we will not, as a general rule, do a whole lot with these 2 equations. This is the calculus space course. We do a lot more with these. And 152, there's more of, here's the situation, here's the formula, which is unfortunate. But there's far more calculus involved in magnetism than there is in electricity. So, that being said, let's talk about the magnetic field a little bit, and then the video that you're part of the Grammarly ad for. So if I have a north and south pole here, the magnetic field external to the magnet comes out of the north end, curls around and goes into the south end. And you just draw these lines so you sort of get tired of it. Similar to electric fields, the greater cluster of lines you have, the larger the magnetic field. Internal to the magnet, the lines are going from south to north. It's just continuous. If I have a charge, so I have some charge here, and I wrap a Gaussian surface around it, I have this formula that the electric flux through a closed surface is equal to that internal charge over epsilon sub naught. Because I can have an electric monopole, so I can have a charge just by itself, but I can't do that for here. No matter what surface I draw, I have just as many lines going in as going out. This is Gauss's law of electricity, Gauss's law of magnetism. The magnetic flux through a closed surface is equal to 0. Because for every north, I've got a south right next to it. Until someone finds a monopole, magnetic monopole. I did hear the story once when I was in grad school that there were some grad students decided to play a practical joke on their professor, and they faked the data to make it look like he found a magnetic monopole. As a grad student, it was incredibly funny. Not being a grad student anymore, it just seems cruel. Now, let me provide some evidence that some of this stuff actually is true.
Loving the multimedia today.
Nothing but the best. If we were in the other room, I would have pulled our thing out and done the demonstration. But, I guess you want to need to be able to see it too.
The generations to come might also be interested in this.
Yeah. That's right. Or maybe this will get it banned in various countries.
Oh, right, you're right.
Okay, it's not going to catch all of it, but it'll catch enough of it. So right now, this is it's some sort of oil. That there's the little black things are iron filings, and so you basically, if it hasn't been used in a while, you have all the black filings are sitting on the bottom of it, and you just shake it up so that the iron filings are now sort of mixed throughout. A magnet is going to be put into here, and then you get to see what happens to the filings. So the magnet has been put in. There you go. Magnet's being put in. And you immediately see that the filings are starting to form patterns there. So you can see the lines forming, going around like that. And lost, okay, there we go. And so I don't know if that's the north end or south end, but it's one of the ends of it. And you can definitely see there's something that is looping around. And apparently putting the volume on didn't do anything. Or wasn't necessary. And we'll say the advantage of this over the one that we have is that we have a leak in ours, and so there's an air bubble that messes it up. Anyway, some evidence that what I've been talking about, there seems to be something there.
If they were to quickly bop the magnet out, oh wait, they're going for it.
So now the gravitational force becomes dominant and it falls. All right. Oh. Oh, there we go. I'm so used to the on button being on and off. Questions? All right, so if I take a material that is a magnet, recognize under a normal atom, under normal situations, the electrons sort of go around the nucleus in some random pattern. And so in a typical non-magnetic material, I got an electron circling one atom creating a magnetic field, and then I got one and another one creating a magnetic field. And typically in a non-magnetic material, there's a lot of canceling out. It's completely random the way that they're oriented. It doesn't have a magnet, but if I can create a magnet, basically I have enough electrons all going in the same direction in order to create an overall magnetic field. So let's take a look at now obviously magnets attract or repel. They also affect moving charges. So this is the force on a moving charge. From a magnetic field. Well, it requires the three things are right there in the description. One, there's got to be a charge. Two, it's got to be moving. And three, there's got to be a magnetic field. So F is equal to Q V cross B. So let's take a look at it from a conceptual point of view before we actually start plugging numbers in. A bunch of dots. What does this represent?
A field.
Pardon?
A field?
Okay, it's a magnetic field in this case, but why a dot? What is that telling us?
Is it charge?
No. No.
I'm sorry, could you repeat the question?
I was asking, what do the dots represent? We're dealing with a vector here. I got dots to represent this magnetic field. I was hoping there'd be some remembrance of this from the past.
I want to say
Part?
it's like,
Wait, sorry?
No.
I heard two voices. Brooke?
he said particles. I was gonna say like, this is like the north or south end in the magnetic field, right? So I want to say it's kind of like a proton or like an electron in an electric field, but I don't know if that's a thing.
No, okay, all right, let's change gears. These are not particles.
I think this had to do with when you were talking about sound or light, and you were using the dots to represent like a density, but it wasn't actually an object. It was more like a visual representation of like, I don't know if density is the right word.
Yeah,
The strength.
that's not what I was going for. I was
Oh.
trying to put them sort of randomly scattered. I wasn't necessarily going for a cluster of dots. Assume that it's a uniform magnetic field for right now. So the dots are, the density at any one point is close enough to another. All right, so when I'm doing the dots, and I'm gonna be doing dots a lot, it's a direction. If I'm working on the board here, I got I hat and J hat, that's simple enough. I can put I hat in any direction and J hat in any direction, but on a board, it's simple enough to, an arrow, I hat's that way, J is that way. But when we have to represent a third dimension, and we do, when we get to this, when we're doing a third dimension, we need to somehow indicate that way or that way.
Oh, into the board, out of the board?
Yep. Which one is this?
Well, if you're looking at the arrow
That's
and it's going away from you, you see the tails, that's why it has an X. And it's going towards you, you see the point on the arrow, so it's a dot,
Yep.
right?
This is coming at you.
And you just circle it? See
If and something like this, if I just am defining the axis, I typically circle it. If I'm defining a whole space like this, I don't typically circle each one. I just leave it like that. So this is coming out at you. So this is out of board would be the more traditional way of wording it. So we're representing a third dimension, and the arrow analogy, for those who haven't had me or it's been too long, the arrow analogy, if an arrow is coming at you, you see the point. So if this is coming out at you. If it's going away from you, you see the feathers, and so into the board would be X's. Now typically in the board, I will do dots because it's a lot easier to draw. Tests, I could go either way, because, well, either way I'm gonna create one and just do a whole lot of copy and paste. So into this, I'm gonna have a proton shooting into this field. When it first enters the field, what is the direction of the force? So we come up here. So the force is equal to QV cross B. The direction of this would need to be the same direction as that, because Q is positive. Yes?
Since it's perpendicular and since that's a cross product, does that mean that the velocity times the magnetic field is like 1 or 0 or something?
As long as the velocity of the particle is perpendicular to the magnetic field, then we're at sort of maximum force.
Oh,
I think we're out of sync here.
I think so, okay, because I was thinking, with the dot product, it's ideal for things to be, because one's ideal for it to be like perpendicular and one's ideal for it to be
Parallel.
parallel, right?
Yeah. Dot product, parallel. Cross product, perpendicular.
Right, so if the proton is going into the left and the magnetic field is coming out of the board, then it's perpendicular.
Yes. So two things. One, the force on this proton will be at a maximum for that charge and that magnetic field. And the other part is, what is the direction of the force?
Would it be J hat? Because I cross K is J?
Ah, going that route. I cross J is K. I agree with that, but what's the direction of the proton?
The direction is moving in the proton's moving in the negative I hat direction,
Negative I hat cross.
positive K hat.
Yeah.
What is negative I hat cross K hat?
I guess that's different from I hat cross K hat. I don't remember, I remember how to use your IJ, KIJ, but
All
I
right.
don't remember.
So what is I cross K?
I cross K is J.
Is it negative J hat?
Oh, yeah, that would make sense.
If I cross K is,
Right.
yeah, so,
Gotcha.
or, alright, so when trying to determine directions, it's sort of a mix here of, there's those moments of going, alright, you remember it, and then there's those moments of, yeah, not everyone's speaking here, so. Let's do a quick review. So if I go in IJK order, right here, then my cross product is positive. So I cross J is K, J cross K is I, K cross I is J. So these are positive. If I'm going in that direction, it's negative. Order matters. So I cross K is negative J.
What?
So you were right
Oh,
when you
that's
said
right,
J
but
hat.
For the wrong reason.
Yeah.
Okay, weird.
All right, there's the right-hand rule. There's gonna be many right-hand rules. Let's bring this one back or acquaint you with it, whichever one's appropriate. When you're doing a cross product, the way that you determine the direction conceptually is you put your hand in the direction of the first vector. Our first vector is V. So if I put my hand in that direction, I got 360 degrees of orientation here. In order to determine what is the one way I want my hand oriented, I want it so that when my fingers bend, they bend in the direction, towards the direction, the fastest way of the second vector. V is coming down at you, so I do it like that. And my thumb points upwards. So the cross product of this velocity and that magnetic field is up, which is J hat, given that definition over there.
It's just always been confusing to me.
I think the little cheat with the IJKIJ makes a lot more sense out of context for some reason. Yeah.
If that works for you,
I love that.
Yeah.
you get the same thing.
That's just what I'm gonna go with,
There's another rule of doing the exact same thing. It all stems from the right-hand rule. It's another right-hand rule. It's the Sten gun approach. Sten gun, that's the one that you've got, it's a machine gun, you've got something to hold on to over here and pull the trigger. You see it in World War II movies, big British commandos.